Hi, welcome to my talk. And first of all, I would like to thank the organizers for giving me the opportunity to give this talk. Icy conditions in protoplanetary disks, how and where to find your water snowline. So let's first take a look at snowlines in disks. Very close to the star is very warm, so all your volatile species are in the gas phase. And if you go further out, then water is one of the first species to freeze out, which happens around what you call the water snow surface. And the midplane radius where this happens is what you call the water snowline, which in typical Ori and Herbig disks is located between 1 and 10 AU. And if we go even further out, not only water is frozen out, but also CO starts to freeze out at what we call the CO snowline, which is located between 10 and 100 AU in those disks. So based on these numbers, we can already say that the water snowline is difficult to resolve as ALMA, yet it is very important for the formation of planets. The freeze out and absorption of water around your water snowline also increases the surface density in that region, which means that there's more material available to form planets. And also the streaming instability can be triggered, which means that it's easier to form larger bodies. And not only that, it also affects the chemical composition of the planets that are forming in the disks. If you look at this figure, we see that the C/O ratio in both the gas and in the grains changes around the major snowlines such as water, CO2 and CO, which means that if we form a gas giant over here, it will have a different chemical composition than if we form it over there, which is something we can hopefully trace as exoplanet observations. So let's first take a look at the CO snowline. How do we actually find it? Because CO is optically thick very often, which means that we cannot see the midplane where CO freezes out. And that's also what you can see over here. You have CO observations in TW Hydra, and they're sent to repeat, but CO is detected everywhere in your disk, essentially. So in order to still find the CO snowline, we use a chemical tracer. The chemical tracer is a molecule that's somehow related to gas phase CO. In this case, N2H+, which is destroyed by gas phase CO. So inside CO snowline, we don't expect any N2H+. But outside CO snowline, where CO is frozen out, there's nothing or very little to destroy N2H+, so we expect to see ring-shaped emission, and that's exactly what has been observed. Ring-shaped emission of N2H+, where the inner rim is correlated to the CO snowline. So that's CO. How do we do it for water? Well, I already told you that we need ALMA to resolve the water snowline, but it also means that we need to find a way around our own atmosphere that's observing emission from water from astronomical sources. So that's why we're using a chemical tracer for the water snowline. And this chemical tracer is HCO+, because it's destroyed by gas phase water via this reaction. HCO plus HCO becomes CO plus H3O+. So based on this reaction, we expect HCO plus to be abundant outside the water snowline, where water is frozen out. We expect it to be depleted inside the snowline, where water is in the gas phase. So let's see how that works in typical Herbig disks. But before I'm going to do that, we also need to think about what's different between the CO snowline and the water snowline. The major difference, or one of the major differences, is that the water snowline is located a lot closer to the star. So there are three things affecting HCO+. First of all, the water snowline. But second of all, the dust in the inner regions of the disks becomes optically thick, which can mimic the effect of gas phase water on your HCO+ emission. And we also need to think about the molecular excitation of HCO+. So let's first take a look at the first point, the water snowline. Here I'm showing you a model of a typical Herbig disk, where we have the radius on the x-axis and the HCO+ column density on the y-axis. And in this model, the water snowline is located around 5 AU. And inside the water snowline, as you can see, we have very little HCO+. And then the column density increases by a lot when we go outside the water snowline. So that looks very good. More or less also what we expect. But if you then look at the emission, it also looks very good. You have very little emission in the inner parts. You have a lot more in the outer parts. So far so good. But still, are we actually seeing water snowline or not? So in order to check this, I'm going back to my column density. And the model I showed you before is called water, because water is included in the network. But I'm also showing you now a model where I excluded water from the network. So there's nothing to destroy HCO+, or at least no water. So HCO plus can exist everywhere in your disk. And that's also what you can see if you look at column density, it just keeps increasing towards the star. So we have a very large effect of water on the HCO plus column density. But if you look at the emission, the effect all of a sudden is very small. So something is causing a lack of HCO plus emission in the inner part of the disk, regardless of whether or not you have snowline. And that brings me to the second point that I mentioned before, the dust in the disk. And in order to see what the effect of the dust is, we ray trace the model without the snowline, so where we have HCO plus everywhere in the disk. We ray trace that in a model where we lower the dust opacities by a lot. So we essentially remove dust from the model. And what you can then get is this red dotted line. And if you compare to the red solid line, you see that there's a very big difference, especially in the inner parts. And that is because dust is optically thick in those regions, which is mimicking the effect of the water snowline. But still, this dotted emission is still ring shaped because we're still missing some flux in the inner parts. And that's because of molecular excitation. The inner parts are too dense and warm to highly populate the JS2 level. So there are some catches if you want to use HCO plus as a tracer of the water snowline. But there is hope, because I also looked at what the emission is of this blue line, where we included the water snowline, if you have very little dust. Now we get the following. We see that outside the water snowline, the two dotted lines are very similar. But inside, there's a huge difference, or at least very big. So if you find a disk with very little dust, you can use HCO plus as a tracer of the water snowline. However, those disks are a bit rare, but luckily for us, the universe is not only filled with quiescent Titorian Herbig stars, we also have outbursting sources. And V883 Ori is an example of that. It has a very high luminosity because it's outbursting. And that also heats the disk, which shifts the snowline to much larger radii where the dust is not that optically thick. And it's a lot easier to observe. And because this is such a good target to find the water snowline, it has already been localized before. Not as HCO plus, but for example with dust. Because a very abrupt change in the continuum emission is observed around 42 AU, indicated by this black ellipse. And that has been attributed to the water snowline. But also complex organic molecules have been used. We think that they're related to the water snowline because the desorption temperature of complex organics, such as methanol, is similar to water. So if we see those, water should also be in the gas phase. And finally, we could of course also use HCO plus to find the water snowline. But let's first take a closer look at what the literature values are saying. Here I'm showing you a radial cut of the continuum that I just showed you. And you can see that it has a very abrupt change around 42 AU, which is probably due to the water snowline, according to this paper. But methanol observations show something different. Methanol extends further out, and the authors think that it could be consistent with a snowline at 42 AU, but it's more likely that the water snowline is located around 100 AU. So these values are very different. And we can use HCO plus to actually resolve this discrepancy and see which one is more likely to be the case in this disk. So here I'm showing you the HCO plus observations in V883 Ori. You see beautiful ring-shaped emission. There's very little emission in the inner parts. But the first thing we need to prove before you can do anything else is that this is not solely because of dust. And that's why I'm showing you again the methanol. This methanol line is likely optically thin, which means that it's tracing the midplane. And that also means that this drop seen in the HCO plus emission is likely not solely due to the continuum, and we also see a contribution from the water snowline. So we built a model, modeling the HCO plus emission for 3 different snowline locations. The first one is very close to what has been observed for the dust, and the second 2 are closer to what has been inferred from the methanol observations. And here I'm showing you the first one. Snowlines at 47 AU, which is close to the radius which has been observed or inferred from the continuum observations. And you can see that the HCO plus emission in the outer parts works quite well, but in the inner parts it doesn't work that well. And the inner parts are important to find the water snowline because that is where water has an effect. Then if I shift my snowline outwards to approximately 80 AU, you see that it starts to work better in the inner part. And if you move it to 120 AU, it's working even better. You can also see that the peak is moving outwards, which means that also in our model, we're actually seeing the water snowline. So based on these models, we expect the water snowline to be located at approximately 100 AU in this disk. And if you then compare it to the literature again, we are consistent with the radius derived from methanol observations, but we're not consistent with what has been observed from the dust. So based on this and our analysis of the data, we think that the abrupt change in the continuum at 42 AU is not related to the water snowline. So in summary, the HCO plus abundance jumps by 2 orders of magnitude around your water snowline, but it's tricky in the Ori and Herbig disks because of the optical depth of the continuum and molecular excitation. However, our analysis of the V883 Ori data suggests that the snowline is located at 100 AU, and that is unrelated to the abrupt change in the continuum observed at 42 AU. If you have any questions, please feel free to ask. Thank you for listening. Goodbye.